Okay, everybody. So this is week 3, lecture 1. It just says lecture 3 here, but what we're going to be covering is for loops and some plotting. So we did a little bit of plotting already, just to have something to do last week, but we're going to learn a little bit more about it now. So although the main topic is probably for loops. So let's just go ahead and jump into it. So if you scroll down here, it says the for loop is your go-to tool when you know exactly how many times you want to repeat a block of code. So that's the key there, right? We want to repeat a block of code. And if you look here, I mean, I should have put this in a box or something, but the syntax is for and then index, but this is a variable name. So you can put whatever you want there and then equals, and we do start value colon step end value. And that's exactly the syntax that we used when we were creating a vector before. And you'll see that when I write an example momentarily. And then inside, I say inside because we're going to have a section of code that is inside the for loop. And then when we're done with the for loop, we're going to end with the word end. And in here, you put the code that you would like to repeat. So the whole point of a for loop is that you can repeat a block of code a certain number of times. With just this much said, I want to head over to Octave, which should be running somewhere. Here it is. And we'll go ahead and I'll make a new script, and we'll put some code in here. So just a reminder, last time we did do something like this, right? Like x equals 1 colon 5. And that would mean, hopefully we understand, if I do print x, I'll actually put a semicolon on the end of that. Let's save this. File save as. Let's call it script 2. I don't know. And I've got the command window down here, and I could just hit the play button up here. So I'll do that. What? Oh, I did. I wrote print like I'm doing Python. Oopsies. That should be display X. Okay. So actually, what I'm going to do now that you're probably not going to see is I'm going to hit pause on here and fix something. Okay, I'm back. Hopefully that didn't take up any time for you. So anyway, back up here, we have just x equals 1 colon 5, display x, and that just displays the numbers 1 through 5, right? And the syntax that I used up here to get that x is exactly the syntax we use for the for loop. So if I were to do this for, oh, I hate that color. I'm going to pause it again and fix that. All right, we're visible. So for, and then you use the syntax that we used before. So I could even write like x equals 1 colon 5, like I did when I was just creating the numbers 1 through 5. And then you'll notice that when I hit enter here, it indents me a little bit. And that's because in a for loop, you want to kind of keep track of what code is inside the for loop and what code is not. And we do that by indenting. And so we write for x equals 1 colon 5. And then if I just do this, display x, and then end, and that should be lined up with the for. So that's why I moved it over manually. It was here, but I did that. Then what you'll see is something slightly different than 1, 2, 3, 4, 5 horizontally here. You'll see 1, 2, 3, 4, 5 vertically here. And so what's happening in this code is that x is going to be 1 through 5, but it's going to take on each of those values once per time through the loop. So basically, the first time through the loop, x is 1. The second time through the loop, x equals 2, right? And then, dot, dot, dot. And then eventually, the fifth time through the loop, x equals 5. And we're going through 5 times because we picked that we wanted to start our loop at 1 and end our loop at 5. And then each time through the loop, we're displaying x. Now, we didn't have to display x. We could do anything we want here. So like I could have said display hello like that. And let me just clear this. And if I run this now, you can see that it prints hello 5 times, right? We don't have to do anything with x in here. The point is that x is going to take on each of these values from 1 through 5, and we're going to repeat the section of code inside of the loop one time for, each of those times. So a for loop repeats a section of code, and you can repeat any section of code that you want. So you can put whatever you want in here. So like I could have said like um, A equals 17, right? And then here I could display the A, and then after I display the A, you can definitely have, you know, a bunch of lines inside of a for loop. What do I want to do? I don't know. Let's do this. Let's do A equals A times 2. So we're going to multiply A times 2. Let's see what happens. So now it says 17, 34, 68, 136, 172, right? So what it's doing is it's multiplying by 2, right? 17 times 2 is 34. 34 times 2 is 68. 68 times 2 must be 136. 136 times 2 must be 272. And so we're looping through this 5 times, and each time through the loop, it's displaying whatever the current value of A is, and then it's multiplying A by 2. And so any task that needs to be repeated a certain number of times can be made with a for loop. Okay, so you can use that for a lot of different things. We'll see a couple of examples of it. So here's an example. We could find multiples of 13, and the problem statement is here. Let's use a loop to scan the numbers 1 through 100 and identify which ones are divisible by 13 using the mod function. Now, this is our first use of the mod function in this class, um, but I'll show you what it does. So it says the logic, if the remainder of n divided by 13 is 0, the number is divisible by 13. So try to remember that, right? If you divide by 13 and the remainder is 0, then the number is divisible by 13. Okay, that's what like divisible means. And you can compute the remainder using this mod function as it says up here. Now let's see what that looks like. So I'm going to go down to the command window just to type a few commands. So if I type mod and I type any number and a 13, we'll see what happens. So like if I do 10 comma 13 here and it says 10, all right. If I do 11 comma 13, it says 11. If I do 12 comma 13, it says 12. And if I do 13 comma 13, oh, look at that, it's 0, right? That one comes up 0 because when you divide 13 by 13, the remainder is 0. If we keep going, mod 14 comma 13, we get 1 because when you divide 14 divided by 13, you get a remainder of 1, right? 13 goes into 14 one time, and the remainder is 1. And so if we pick different numbers here, like let's say I pick, you know, 22, right? Then the remainder is 9 because 13 goes into 22 one times, but the remainder is 9, right? And if we sneak up on, I guess the next divisible number would be 26, right? So if I put 25 here, I get a remainder of 12. If I put a 26 here, oh, look at that, it's 0 again. So 26 divided by 13 has a remainder of 0. Because 26 is divisible by 13. So that's the whole key. If I keep going, right, now we're back to a remainder of 1. So you can just check any number to see if the number is divisible by 13. Now, I guess we're kind of doing this out of order here, unfortunately, as I'm saying this, because we haven't talked about an if statement yet. But if we try to do this, what can I do? Let's get rid of this A. Let's get rid of all this. So if I have, first of all, this says we want to go from 1 to 100. So we should try 1 through 100. Now, of course, if I just display the X value there, um, then we're just going to get all the numbers from 1 through 100, right? So all those printed out. And what we wanted to do was I wanted to just print the ones that were going to be divisible by 13. And unfortunately, or fortunately, that takes what we call an if statement. And we haven't talked about if statements, so I'm doing this in the wrong order here. So maybe you want to ignore this for the moment. But we saw that if you display all of the numbers, right, with display X, you get all the numbers from um, you get all the numbers from 1 through 100. But what we could do is we could check them and say if the number, sorry, if mod X comma 13, so that'd be 1 comma 13, 2 comma 13, 3 comma 13, etc. If that happens to be equal to 0, then I can display the X. Now you'll notice something interesting here, perhaps, which you'll notice that this end is end if, and the other end for the for loop was just end. That is something that's specific to octave, and it doesn't need to be that way. So if you delete the if, then you can just have if end and for end. You'll know which one is which because you're indenting it correctly, right? And if you do this, then what you can do is, how do I want to say this? You'll be making code that works in MATLAB as well. If it says end if like this, then your code is fine in Octave, but your code would not run in MATLAB because of this extra if here. And so I would recommend just if you remember to, just to take off those ifs, just to make it so that your code would be compatible with MATLAB if you ever took it there to use it. Otherwise, you'd have to fix these little things. It doesn't take a long time, but still. Um, all right. So if I write my code like this and run it, you'll see that now it just prints 13, 26, 39, 52, 65, 78, 91, because those are the numbers that are divisible by 13. Now, that involved knowing how the if statement works, which I think you will know probably before you see this, because in the lecture for week 3, or sorry, in the lab for week 3, I'm going to talk about if statements. Um, so hopefully you'll know about that before you see this lecture. But the main thing here was just to get a for loop going that did something. Okay. Now, the task that our textbook, right? Remember our textbook, I pointed you at chapter 4 in the textbook to look at. Um, and chapter 4 in the textbook tries to show you some things about plotting using loops. And so this is just an example, but I'll change my code here. And so we learned how to make an X vector last time, right? For plotting. So like make an X vector for plotting. You remember that, I'm sure. We can just pick a starting value like -10, what to skip by, so like 0.1 maybe, and how high we want to go for our X values, so like maybe 10, right? So you can make some X's. And what we did before was we just did something like this, right? Like y equals sine x. And that would allow us, um, y equals sine x would allow us to calculate the sine of all of those x values all at once. And of course that works, but they're going to show you a different way. So what I'm going to do is I'm going to, um, let's see, compute the y values in a loop. Now, this is not efficient. This is not efficient, but we can do it. And so one way you could do this, and this is the way that they show it. Is it the way that they show it? I don't know. I'm not going to flip back. One way we can do it is as follows. So um, we could say for, and I'm going to say IDX equals 1 colon, how big does my loop need to be? So I don't know how many entries X has, right? Like it's actually kind of hard to calculate. We went from -10 to +10 and we were counting by 0.1s. So, what is that? So I don't know. So I don't have a stopping amount here. So what you can do is I know that I want to calculate one Y value for every X value. So I can put in the length of the X vector for my stopping place. So then I have the index, that's what the IDX was going to stand for, goes from 1 to the length of X. And I don't know what that is, but it's a number, right? There's a certain number of entries in X, and that will pick it out. And then what I can do is say the Y entry for that particular index should be equal to, I'll do a sign of what? The X entry of the index. Now, before we run this, I'm going to come down here and show you something. So if I go like X equals, just so we're clear, let's say 3 colon 0.1 colon 4, right? I just didn't want them to be 1, 2, 3, 4. So we just have some values here, you see, for X. And so if you do X1, right, you get 3. And if you do X2, you get 3.1. And if you do X3, you get 3.2, etc. Right? So when I do X IDX up here, that's going to be the equivalent of X1, X2, X3, because the IDX is counting from 1 up to the length. So this is going to be X1, X2, X3, X4. So I'm taking X1, X2, X3, X4. I'm plugging them into the sign function, computing a value, and then that value is being stored into Y IDX. So like X1 is going to be stored into Y1. Sorry, the sign of X1 is going to be stored in Y1. The sign of X2 is going to be stored in Y2. And that's going to happen for the entire vector. So when I run this code here, save this and hit run, we're not going to see anything because I put semicolons on the end of everything. But if you look over here, what we should see is that X is a vector with 201 entries, and Y is also a vector with 201 entries. So they match, right? So if this had 201, then the Y has 201. And so this loop actually was able to calculate all those Y values. Again, this is not as efficient as what we were doing before. And then once we do that, we can plot it. So of course I can do plot X comma Y like so. And we just get a simple plot of a sine function. And it looks okay, right? Now, something else we should get in the habit of doing is we should label our plots. And so we did talk about this last time. So you can see you could use the title function, the X label, Y label. If I can maybe copy those. Copy pasting from PDFs will often not copy paste right. So you do have to be careful doing what I just did there. But there we go. We got X values, Y values, and some title. Um, okay. So that was plotting. Now, there's other things we can do that are useful. So for example, there's some commands over here, axis square, axis equal, axis tight. Those are actually going to control the axis of your plot. So just to show you, I'm going to run this. We got the plot here. Maybe I can um, squish this so we can see the plot here. And if you just look over here, if I say axis square, this should change. Ah, made it a square, right? If I say axis tight, um, well, I guess it didn't do anything because this was already fitting the data, but it could have possibly changed the graph if there was some reason. If I do axis equal, then that means that if you have 20 on the x-axis, you should have um, well, actually, I think it makes it so like 5 units on the x-axis is the same space as 5 units on the y-axis. I say five, but it's 1 unit is the equal to 1 unit. So 1 unit on the x is the same space as 1 unit on the y-axis. So maybe now if I do axis type, nope. But if I do square, okay, we're back there. That's actually not the same, not the same. So these can sort of control the plot, but the main way is to use the axis the way it's listed here or here. So axis, parentheses, square bracket, and then you can pick a minimum and maximum x value and a minimum and maximum y value. So that basically lets you zoom into your plot. So if I do axis, parentheses, and then square brackets, close parentheses, and in the brackets, you put your numbers. So like if I did 0, comma, pi, that'd be, I want to show the plot just from 0 to pi. And then if for the y-axis, this is a sine function, right, which goes between -1 and 1. So what if I do like -1.1, comma, 1.1? What does this look like? Okay, so we see it here. So you can see that the y-axis is between -1.1 and +1.1. You can see it just goes a little bit over 1. And you could see that, it hits 0, 0, and then up and then back down. And we know that sine of pi is pi, or sorry, sine of pi is 0. So it comes back down to 0. So if I wanted to show one full wave, that would be between um, 2 times pi, right? So if you want to show one full wave, it's like that. Now, do remember though that it looks like we're showing any portion of the sine plot that we want, but we actually only calculated it from -10 to 10. So if you tried to make your plot go from like negative 20 to 20, for example, it'll make the plot that big, but of course, you don't have any data after 10 and below -10. So if there's no data there, then you won't be able to see it in your plot. But nevertheless, this is very useful to show specific sections of your plot. Like you could zoom in, like we knew that like sine of pi is 0, right? Well, what if I do like negative, sorry, if I go pi minus 0.1 to pi plus 0.1. And then I want to just show like -0.1 to +0.1 on the y-axis, right? Then you can do something like this. And this is just really zoomed into a little section of the graph, right? Because you can see that we're between 0.1 and -0.1 and -3.05 and positive whatever pi plus 0.1, 3.24, I guess. I guess it's from 3.04 to 3.24 based on how I did those x-axis. So you can zoom in right there. Remember that we do have a grid command as well that is kind of useful. Um, and so this is just more stuff that helps you make a nice plot. Now, the last thing we're going to talk about, and I'm going to do this briefly because of time, but we can control the color of things and the style of things. And so there's a few things listed here. So there's colors listed up here. R, G, B, M would be red, green, blue, magenta. There's others. Um, Your lines could be solid lines, dashed lines, or dotted lines. And your symbols can be circles, asterisks, squares. They could also be X's and pluses. They're just not all listed here. And so as an example of that, here's a plot of like the sine function and the cosine function. And you can see from the way that I did this, just look here, it says XY and then R dash dash. And so the R means red and dash dash means a dashed line. So we have a red dashed line for the first plot. And then for the second plot, which was cosine, so X and Y2 was cosine, it says BO. So B means blue, O means plot circles. And we're plotting circles, so there's no lines there. So if I actually take this code and notice I'm not bothering with the for loop here now. What? What? What is complaining about line 4? Oh, it says element by element. Okay, fair enough. So here's my plot, right? And like you can add everything. You can add a color, a line, and a marker style to every one of these. So like this is blue circles, right? But I think if I put like a dash there, I think now we're going to get a line also through those blue circles. There we go, right? And if you change that to a colon, now you have, it's hard to see, but that's a dotted line and circles, right? Yeah, and you can change those to an X maybe, why not? You see you have X's, um, dashed lines, although it's hard to see. So you can do a lot of these things. Like red squares, whatever you want, right? Not whatever you want, but you have a lot of variety in what you want to do in terms of, you know, regular lines, dashed lines, dotted lines, colors, and then if you want to, you can put markers on there to mark the specific points that are on your graph. So that's useful. And I think that's it for today, actually. So I'm going to stop it here, and I will talk to you guys probably in lab today.